Okay, good afternoon. Let's start. So for this part 5 lecture notes, I have added a few slides on this timing related to synchronous circuit. And now let me explain this with 2 examples. First, for a flip-flop, there are 3 important signals. Input D, clock signal, and the output Q. And there are also 3 important timing information. Setup time, hold time, and clock to Q delay. Clock to Q delay was omitted in a previous lecture notes, but now it has been added back. This setup time refers to the arrival of input D and the arrival of the clock edge. It means that the input D must be ready for a setup time before the rising edge of the clock. That's easy to understand. Hold time means that the input data D needs to be steady for a whole time after the rising edge of the clock. In other words, D must be held stable for a period around the rising edge of the clock. It must be ready for a setup time before the rising edge and be stable for a whole time after rising edge of the clock. This has been taught before, but now another important timing information is the clock to Q delay. Q is the output. So when the clock rising edge comes in, it will sample, the flip-flop will samples the input D and pass the input D to the output Q. But let's take some delay. Say now D is high, so the output Q will rise to high, but it will occur after a certain amount of time. I mean, a certain amount of time after the rising edge of the clock. So from the rising edge of the clock to the moment that the output is ready, this delay time is called clock to Q delay. To appreciate the importance of these timing constraints, I have 2 examples in the following 2 slides. Here is example 1. So we have 2 flip-flops. The flip-flop has this timing information. Its clock, the clock to Q delay is 2 nanoseconds. The setup time is 3 nanoseconds. And there's a hold time. A hold time is not used in this example, also not shown. And between these 2 flip-flops, there is a combinational logic block. And it also produces a delay. And this delay varies. It has a range from 2 nanoseconds to 6 nanoseconds. So that's delay of the combinational clock. Now the question is, what is the maximum clock frequency of this circuit such that it can operate properly? Basically constraints that so the signal passed from D to Q And this will involve a delay, a clock to Q delay of 2 nanoseconds. And then it will pass through this combination logic block with a range of delay. And it arrives at the input of next flip-flop. So the arrival of the input of the second flip-flop should be a setup time before the rising edge of the next clock cycle, next clock edge. So consider 2 consecutive clock edges. So within this period, within this clock period, the signal must propagate through the first flip-flop, propagate through the combination logic block. And yet it needs to be a setup time before a second rising edge of the clock. So that's the constraint imposed by the setup time. We can write this equation. So clock period should be longer than the maximum value of these 3 elements, the sum of these 3 elements. Clock to Q delay, 2 nanoseconds, logic block delay, and the setup time. So clock period should be longer than the maximum value of this sum. Otherwise, the setup time may be violated in some cases. So in order to ensure that this inequality is valid for the worst case, then we can put the worst delay to the logic block. So we have 2 nanoseconds plus 6 nanoseconds for the worst case of this block, and setup time is 3 nanoseconds before the edge of the clock. So it means that the clock period should be greater than this. So minimum clock period is 2 plus 6 plus 3 equals to 11 nanoseconds. So that's the minimum clock period. And the frequency is the inverse of clock period. Means the maximum clock frequency allowed in this circuit is 1/11 nanoseconds, is 90.9 megahertz. So the clock frequency cannot be higher than this in order not to violate the setup time constraint. Okay, you get the list. Now let's have another example to check the hold time constraint. In this case, the circuit is slightly different. I have a clock buffer between the 2 flip-flops. This is frequent. Sometimes you just have a clock buffer to drive the clock. Now I have a clock buffer here, which has 5 nanosecond delay. Now, 2 flip-flop has a clock to Q delay of 2 nanoseconds. The setup time of 3 nanoseconds and the hold time of, say, 1 nanosecond. The data D must be held valid for at least 1 nanosecond after rising edge of the clock. And this combination logic block has a delay ranging from 2 nanoseconds to 6 nanoseconds. And the question is, what is the maximum clock frequency of the circuit due to the hold time constraint? We consider the hold time. Maybe I draw a graph here, timing graph here. So this is clock to the first flip-flop. and the clock to the next the second flip-flop is delayed. Not delayed. This delayed. Okay, let's consider first edge. This is first edge here. So this clock so the input D to clock 2 must have value after a whole time. For a whole time after the rising edge of clock. The D should not change. Which means that the input should not the clock figure should not be too high, I think. Maybe this is not to the scale. So the next let me extrapolate the situation. Suppose this whole time is like this. This is whole time. Whole time. So the clock, like the input to the second flip-flop should be held constant for a whole time after rising edge. Here, that means the next sample should not cause a change in the input of the second flip-flop. Next sample should not propagate. Next sample should propagate later than this time. So the fastest possible arrival of the next input at this point should not occur earlier than the whole time after the present rising edge of flip-flop 2. So we can write an inequality clock period, which means here suppose so this is the next input is to receive next input. So we have a clock period here plus the faster delay from this point to D. Clock to Q delay of first flip-flop plus logic delay. So this faster delay plus 1 clock period should not be sooner, should not occur sooner than this whole time. This whole time plus should not occur sooner than this whole time plus this delay between 2 clock cycles, between 2 clock signals. Okay, so the on the right side of the inequality is the present clock edge of flip-flop 2, present clock edge, present rising edge of clock, present rising edge of the flip-flop 2. So it's a T buffer later than the first flip-flop's rising edge. Plus the whole time. So this should be a smaller than 1 clock period plus the faster delay. So you get, see, do you understand the meaning of this inequality? Okay, still use this graph. let me redraw this. Let's draw faster problem. So this is a default one. Default one's clock, default two's clock. But because of the buffer, we have delay here, certain delay. And now there's a whole time after this rising edge, the whole time is this. It's whole time. Okay. Which means D here, D2, let's call this D2. D2 should not change. This here, D2 should be steady in this time period. Right? D2 should be right. It's whole time constraint. But it is possible that the next signal, next input here may disturb the signal here. Right? So the next sample is here for the next sample. So next sample, next input could propagate. Say next sample comes here and it has two delays, clock to Q delay plus logic delay. It should not occur sooner than this time, right? Otherwise, it will ring the input of the second Q4. I hope you can get this. I think you get it, right?
If we consider the setup time constraint of this case, I think the period may be longer.
Yeah, we have two constraints. Then we choose the in this case the constraint is less stringent than the previous case. Is this your question?
No, I mean, if I let's say like the previous case, like example one, the setup time constraint, and I think that maybe the period is even longer than this whole time.
The answer is here.
Yes.
Yeah, in this case, the situation is not bad. You do not need to worry about this whole time constraint. But in some cases, you say this is very long, you may need to consider that. I'm just showing you. It's possible after the second sample from the second sample here, second sample or the next sample may arrive at this point earlier than the time allowed for this people to process first sample. This has a time interval to process first sample. And the next sample should not occur when this FIFO2 is processing the previous sample. Right? I think you can. Well, this is not hard to understand. You just need to be careful. So we are talking about the second sample may arrive too soon to the input of second FIFO. If it is too soon, then it will violate the whole time constraint. Okay, the numerical answer is here. Period. The period here means the coming in of second sample, and plus the faster delay should occur later than one whole time after the rising edge of the second flip-flop clock. Now we put in the values. So the minimum value of this C clock and T logic is this is 2. T logic minimum value is 2. Move this to the right hand side. So clock period should be greater than T buffer plus T whole minus this 2 plus 2. So it's 2 nanosecond. So minimum clock period here is 2 nanosecond, and this translates to a maximum clock frequency of 500 megahertz. Now you have two constraints. This says maximum should be less than 500 megahertz. The other constraints, earlier constraints says should be lower. I mean, should not exceed 90.9. Of course, this is the actual constraint. Right? You need to fulfill both constraints at the same time, but now one is more relaxed, the other is more stringent. This is more stringent. Okay. All right. Are there any other questions? Okay, so let me go and move forward to the adder part. We've discussed this. A single bit full adder basically has 3 inputs, 2 outputs. And straightforward implementation of a multi-bit binary adder is to cascade 1-bit full adders in series. So the carrier bit is connected in series. The carrier bit here, a carrier signal. So in the worst case, the most significant bit needs to wait for the arrival of its carry in. I mean, worst case. I mean, it needs to wait for the propagation of the carrier all the way through these stages. So the worst case delay is expressed by this formula. So in the worst case, the carrier needs to propagate the first stage, second stage, and third stage before arriving at the input carrier input of the fourth stage. So there are 3 carrier delays, or n-1. N is number of bits. And then it produces output when the carrier in arrives. And this is another delay. Let's call it the T sum. So here T carrier and T sum are the delays of 1-bit full adder. So imagine that you have say a 32-bit LAN. In the worst case, the carrier needs to propagate for 31 stages, 31 full adder cells. That could be very long. So that's the critical path, longest delay. And to overcome this long delay problem, many adder topologies have been invented. And next, we will go through a few of them, a few of important solutions. This has been discussed. Most of them based on this the use of intermediate summing signals. So we have ABC as input, and we can say generate 2 intermediate signals, G and P, generate and propagate. D is not necessary. But anyway, you need two of them. So let's just consider G and P. G and P. G and P are only function of A and B. They do not need to wait for carrier input. So G and P can be obtained immediately, or not immediately, and very soon for each stage. They do not. This is G and P do not need to wait for carrier in. So G and P are only function of A, B, and not function. They are not functions of Ci. So they generate and propagate. Can be made available very soon. Then we can express the carrier output and the sum output as function of this GP as well as carry in, as shown here. So this GP are intermediate signals. They are just functional AB. Then CO and CS, carry out and sum output. They are function of both G, P, and the carrier input. Carrier input. Now, let me show you the first fast adder topology. It's named as carry bypass adder. Now let's consider one stage of a carry bypass adder. I say it's 4-bit. 4-bit. We have 4 full adder cells, and we use P, G, and C as input for each full adder cell. Not A, B, and C, but P, G, and C. Okay, the idea here is that the worst case is the situation that the input carrier needs to propagate through all the 4 stages here to the output to the next stage. That case occurs when P0, P1, P2, P3, the propagate signal of all the adder cells are high. Right? The propagate. Worst case occurs when P0, P1, P2, P3 are all high. So now we create a multiplexer. So when this, so we have a signal. So this multiplexer is led by this P0, P1, P2, P3. If they are all high, then we just bypass the carrier in to the carrier out directly without going through this internal full adders. Okay, well, for one stage alone, there's no advantage at all. But we can you see the advantage later when we have several such stages putting together. Okay, so the idea is to improve the worst case carrier propagation. So when worst case occurs, the carrier just bypass is just skipped these 4 adder cells, and is led through the multiplexer to the output, right? And this can be very quick, right? Not ripple through each adder cell. So this is if the worst case does not occur, then say maybe worst case say this is still a lane, the delay will be or if it is not worst case, then it's another story. We're trying to improve or short-term delay for a worst case. As a designer, you need to consider worst case. The clock frequency cannot be too high to ensure every possible situation is entertained. Okay, so this is a carrier bypass, also carrier skip stage. Now we consider, say we have a 16-bit ADA. We divide it into 4 stages. Each stage is like this. In each stage, we have a 4-bit ADA. 4-bit ADA. Like before, so in each stage we have a setup. Setup is to generate the G and P signal, G and P, and a carrier propagation like this, basically. So we need to set up the G and P and this cell, and finally to generate the sum output. So in one stage we have this setup, carrier propagation, and sum, and a multiplexer. Now, the carrier propagation cannot be skipped for the first stage. And the first stage, say each stage has m bits, and now we have n of m stages. So the worst case is that the carrier propagates from bit 1 all the way to bit 16. Propagates there. And now this can be detected. If this occurs, it can be detected here and here. So in the second stage, we can bypass the carrier propagation, bypass this this stage. So the carrier can be fed to the third stage through the multiplexer, and it can be fed to the final stage through the multiplexer. So the carrier propagation does not need to go through this and this in the second and third stage. So the worst case is like this. The signal goes from here to here, and through this multiplexer, and here, shaded here, multiplexer, here, a multiplexer, then goes into the last stage. In the last stage, you cannot escape the carrier propagation. No. And then you generate a sum. So in other blocks, you also have the sum, but this sum occurs earlier than the worst case delay. So in the worst case, the delay is like this, as I shaded, from here to the multiplexer to here, and to the carrier here, and to the output. Now we can calculate this worst of this critical path. This delayed of the critical path. It has setup time to generate a P and G for each bit, and this is quick. It does not depend on carry in. So we have setup time here, and for the first stage, the carrier needs to propagate through all the stages because it's first one. And so it's m bit. So we have m times t carrier delay. T carrier is the delay through a full ADA cell, carrier delay through. And then it passes through 1, 2, 3 multiplexers. So here we have 4 stages. N of m is 4. So 4 minus 1. So we have 3 stage, 3 multiplexer or bypass. So the T bypass is the multiplexer's delay. And to the last stage, the carrier comes in for say this is 4-bit. So the carrier comes to so this is the just you treat it like a ripple carrier adder. Ripple carrier adder, the delay is this. M-1 T carrier plus T sum. It's M-1. Because I say if we don't care about the C4, so the carrier just propagates through 3 stages, except the last stage. So here, this is the delay of the last stage, last group of bits. So it's M-1 times T carrier plus T sum. So this is last stage. We have 3 bypass logic. So this delay and the first stage. So that's the delay in such a carrier bypass or carrier skip adder. This is to improve the worst case delay. Do you get the idea? The key thing is here. In worst case, you need to bypass. Normally, you need to propagate through this one, but this, in worst case, you notice because P0, P1, P2, P3, this product equals to 1, and its P's value can be obtained very soon. It does not need to wait to see. So this can whether or not to bypass it can be known very soon. So when we need, in the worst case, it is just bypassed, bypass these internal carrier propagation stages. At the same time, of course, this needs to work. There are bypass stages to produce intermediate sum, but this is just one stage. One stage is its delay is confined to this number, the last 2 terms of the equation. And the critical path, and longest delay here is this. It's shaded here. So any questions?
The next before the reset that they take they all bypass it and go to the last curve to they go to the area.
I mean, worst case we bypass. Worst case we bypass. If it is not worst case, then it's just I mean, so consider individual stage. Individual stage, the delay is less. Individual stage is less. Individual group, I mean, individual group, the delay is given by the last 2 terms. All right. But when you consider the worst case, the carrier propagates from B1 to B16, normally it propagates through the intermediate adder cells. But now with this detection of bypassing, we can skip some adder cells for the propagation of carrier.
All of them are skipped.
Yes, for all of them are skipped. That is the longest one. That's the longest delay. And if it is not longest, maybe the critical path is like this. From here to here to here to here. It will be shorter than this. This is worst case delay. Longest possible. All the other cases will be smaller. The delay will be smaller than this equation. You mean this? Note that these 4 stages are operating in parallel, same time. They don't need to wait. The third group, you don't need to wait for the second group. The waiting cases only occurs when the carrier in needs to propagate from bit 0 to bit 16, 15. But this is detected and can be bypassed. T bypass is the propagation delay of this multiplexer. From input to output, it takes some delay for any logic. It's the propagation time of this multiplexer.
There's the first three adder in the carry or the series adder, then it will be, for example, n minus 2 times t carry, and then may be larger than 2 bypass.
Yeah, but in that case, it does not need to wait for this carrier to go in, right? It happens at the same time when the first stage is operating. They're doing things in parallel, all right? So you can consider, this last stage plus a setup time. Setup time is not considered because of obvious reason. You just consider one stage. The delay is given, is fixed, and they are operating in parallel. So the total delay is not sum of them. Only the carrier in, when it propagates through the stages, you need some stage needs to wait.
For example, if it's on the first three adder, the last three adder, for example, the first adder does not have carry out, but all the rest still have carry out, and they are needed for the next stage.
Yeah, they are needed. But because they are doing, for example, the third stage needed to 3T carrier delay. This is smaller than this one, right? Smaller than the generational delay of the first stage. It will be smaller. So this is the longest delay. You can think of different combinations. So and say all this stage, the time consumer is included in this first two terms here. When the first stage is doing things, it's working. They are working in parallel, same time. So it won't consume any extra time when, say, you consider these stages. So I hope you get it. I think some of you get it.
I think the time for the state and the state one is the n minus 1 t carry.
Yes, almost correct. Parts T setup.
Yes, they are not in the n carry.
Yes, M1, you are correct. But the first stage, when first stage, it needs to propagate. Say you have a carry in. I mean, here you have a signal 1 here. You need to propagate all the 4 adder cells. This part is taken from this reference book. If you are interested to read further things, this is one of the reference book. One of reference book of this course is listed in the overview part of the notes. All right, you can read it for details if you don't get it now. Okay, I think and last slide. So here shows the slide to compare the delay of the ripple adder with bypass, carry bypass or carry skip adder versus number of total bits n. For small number of bits, you don't need to use bypass adder, just use ripple adder. You have advantage in bypass adder, say for when n is greater than this range, say greater than 4, greater than 8. Depends on the actual circuit implementation. Okay, I think that's all for today. Any questions? If no, see you tomorrow.